Well, welcome everybody. Welcome to our open discussion on enabling transportation at scale through ML and AI. I'm your moderator, Harrison. Um, I suspect that Amber chose me because in a previous life, I was also working in transportation at a company called Lyft for 5 years. For those of you who may not be from the US, it was a ride sharing company based in the US. And a lot of what I did, my background was, deploying ML models for pricing, dispatching, route creation, and all that. So just unbelievably excited to talk to you both. Um, we're joined here by Holger and Kais, and I'll let them give their own introductions. Maybe start with you, Holger.
Yeah, thanks, Harrison. Super excited to be here today. I'm Holger. I am a manager on the data science team at Archer Aviation. And I guess we'll dive in a little bit more later in what we do at Archer and what I do there. But basically, before Archer, I'll give a little background there. I was in a trucking startup called Convoy, building efficiency into a network of basically matching shippers and trucks. And before that, got my PhD at the intersection of machine learning and optimization applied to energy systems here right around the corner in the Bay Area at Stanford. And before that, actually originally from Germany, got a bachelor's in mechanical engineering. And so, yeah, as you can see, you can kind of find me at like this intersection of data and sustainable transportation and energy.
Very cool. See you representing the Cardinal Red.
Yeah, the red and
Yeah,
the nice Archer logo here, so it matches nicely.
nice. Kais, what about you?
Yeah, also brought my own logo. I'm Kais from Tunisia, and I'm the computer vision engineer at Seafar, which is a Belgian startup operating in the maritime sector. I think we will dive deeper into in details of what we do, but a little bit about myself is I have a automation and control engineering degree, and work experiences were in different sections of the computer vision world. I had an experience with logistics robotics for BMW. Then I worked for a startup uh, that was creating edge AI devices. And later on, I joined CFAR over almost a year ago to apply object detection in the maritime sector, also with edge AI technologies.
Cool. Well, why don't we start by kind of just diving a little bit deeper into Kais, what you were talking about. So I think, based on your description of what CFAR does, I think what I'm thinking is autonomous ships that operate themselves. Maybe walk us through between that sort of very high level idea of what it does to maybe the individual prediction tasks that are going on in the ship. Like, what are they? What are the models responsible for?
Yeah. So what CFAR does exactly is that we're offering mainly a service for shipping companies to assist them in one of the main problems in the sector, which is there's a big lack of sea captains. So what we do is we have a remote control center, a seashore control center, and from here captains can operate multiple types of ships at the same time with 4G and 5G technology. That way you can have a ratio of 2 to 1 or 3 to 1, so 3 ships per captain. So within one shift he can operate multiple vessels and therefore serving multiple shipping companies. That's the main mission of CFAR. But over a year ago, we started look into the potential of having semi-autonomous and fully autonomous vessels. And for this type of technology, computer vision has to be at the core of it. So I joined with the mission to start integrating this technology step by step. And of course, the main goal is to reach the level 5 of autonomy, of course. But for now, what we do is that the role is more for safety and security, in the sense that while we have a captain or a marine traffic controller doing their jobs, the computer vision algorithm will be working in the background to, let's say, replace their attention or point their attention to something that they would have missed with a human eye. So, for example, we're talking about faraway vessels that are approaching, obstacles in the water, but also the presence of humans, as in with kayaks, with yachts, with a bit of rowing boats. So the role now is to enhance the human vision and the human factor of when navigating ships.
Very cool. And maybe for those in the audience who may not be as familiar, like what is level 5 autonomy? Like what is the distinction? And then you know, I think I'm certainly familiar with level 5 as it has to do with cars, but maybe is there any difference between that definition and on board the
Yeah,
ship?
for the shipping industry, it's a very regulated sector, and so to you can't jump from the current situation to a fully autonomous ship. So there are different steps you have to pass by. As in, first you have to start reducing crew
Hmm.
while enabling the capability of remote operation. And then you can have almost zero or like only completely remove captains, for example, from ships and only relying on remote operation. And then we can move to uh, I think level 4 is autonomous sailing, but with a human in the loop and
Hmm.
human monitoring. And level 5 should be fully autonomous and reliable ships.
And so you mentioned previously, obviously computer vision plays a big part of this. Um, would you say, what would you say were some of the unique challenges that you found that were maybe unexpectedly hard uh, in that context?
Um, the all of it. No, but
Nice.
yeah, no, of course it's we're sort of doing a novel thing, as in you can't just run something out of the box. So of course you have to. The big challenge is to collect the data first. That's the essence of any machine learning project. So having a good data collection pipelines and assuring that your data helps your models generalize, and that it can be rich, that can englobe every aspect you might encounter. So that's a challenge. And of course, the way we're operating is that we need to run these model on the edge. So therefore, you have, from software point of view, you need to optimize your model to run, uh, to have it in a on a small size and still hit a high level of accuracy. But also, you need to have the right set of hardware um, to implement in this hard environment. I mean, putting GPUs or computers on a ship has its own offers its own challenges, where you can have a lot of humidity,
Mm, mm.
um, a lot of risk of ruining the devices, and therefore there's this complementing software and hardware and tackling both to have an efficient system.
That's interesting. Wow. When I first thought about it, I was like, oh, it must be easier because you have all this power from the ship. You don't have to worry about a battery, but never thought about the humidity or like the the salinity of the air or stuff like that that might affect the onboard, the compute
Yeah,
devices.
exactly. Delivering a reliable and reliable system is way more complex. And like I said, it's not something that you can run off the shelf or. And we're trying to create a system that's plug and play, but there has been a long way, and there is a long way to achieve that because of different scenarios that you might encounter, different ships and different systems on those ships.
So you mentioned earlier, like part of the challenge is collecting the right data, and I'm assuming with some of the on some of the ships that you have this deployed, it's not only delivering value to the customer, but it's also collecting data as the ship goes along its route. Can you, to the extent that you can you speak a little more to that? You know, I have an engineering background, so I'm wondering, okay, is image data getting tagged on the edge? Are you beaming it directly back to some data center? What's the balance? Maybe just to the extent that you can talk a little bit about that. It's pretty interesting.
Um, the workflow is that from the ships, what you can do on the edge is quite limited. So what I rely on is you have a model running live in real time, um, performing its task, which is, for example, just boat detection. Um, on one hand, you have via our user interfaces that the captains are using to navigate these ships, they can see the results of these models. But on the other hand, we can also use what we use the cameras, but also different types of sensors to trigger data collection, send that data to the cloud, and then further down the pipeline, you use annotation tools and active learning tools to really pinpoint the cases where your model is failing, to know what area or what criteria you should focus on, and then go on to model training and then on model deployment. And of course, it becomes a whole MLOps cycle like most machine learning projects now.
One last question about the data. Sorry, I find this so fascinating. I think probably a lot of the audience out there who, maybe you've heard about some of the vision challenges for self-driving again on the road. You can kind of intuit, okay, well, there's this huge problem. The same stop sign can be in 500 different scenarios, grassy land or asphalt or various weather conditions. I think people might I certainly do, erroneously assume it might be easier in the ocean because it's just ocean and it's blue water, blue sky. Are there similar challenges in the variation of setting? Some maybe a criteria that most people don't think about in this way.
Yeah. Once you have a storm or it's a snowy weather, it's impossible to see with normal cameras. What they do in the shipping industry, normally they rely, like the experienced captains, they rely on radar data usually.
Hmm.
So there you have this sort of limitation on matching the captain's capabilities to see. I mean, of course, that could offer or open up the potential of using a lot of data fusion and collecting data from
Hmm.
other sensor and enforce the image detection algorithm. But again, there are environmental challenges even for something that seems repetitive, like navigating a ship through the ocean or through a canal. But of course, as our model is running in real time, we are always collecting these new scenarios. We're analyzing how it's performing, and then we rely on improving that.
Very cool. So last question, and then we'll move to you, Holger. Sorry. How do you how do you ensure that the models you're building are accurate and reliable, safe to use in ships? Like what are the specific trade-offs you're making in this deployment context that uh, yeah.
Yeah. So a trade-off is, like I mentioned in the beginning, that since we're working with on edge devices and edge AI technology, you have to favor speed over accuracy in a way. So therefore, you might be you're working more on matching the dynamic environment than just having perfect 100% accurate object detection results. But how we are working on improving our models in general is relying on the expertise that we have here. Like I said, I have colleagues from the maritime field. So whether marine traffic controllers, you have sea captains, um, these people have been on the sea or on rivers for years, and they are capable of they are sort of training our model before I train the model. So how it goes is that they are helping me annotate the data. So our big chunks of data, what they do is they assist in the annotation phase. Therefore, we are getting accurate and correct uh, ground truth data. Because if I were just doing it, for example, I would miss multiple vessels, or I'll be confused about certain objects and how they should be classified.
Mhm.
But the experts here, they know what they look at once they see it, and that's something, like I said, that creates really accurate ground truth data
Mhm.
that helps the model become better. And on top of that, what we're doing now is, as the model is doing real-time object detection, the captains, as they are sailing, they are they're monitoring live the results of the model, seeing it on the screen,
Mhm.
and therefore they have the ability to report to us the successful cases, but also the failure cases of our model, and
Yeah.
especially the critical ones. And therefore, we take that into account. We implemented a system that they can in real time save images, like so include that into the data collection pipeline. And
Mhm.
therefore, we have these cases that we can retrain on and improve on.
Very cool.
Yeah. I
Very
think
cool.
I want to just add one thing there. Is like I think Kais brings up like a really great point in terms of just general and transportation. Is there subject matter experts that have worked, in these applications for years or decades, and they have so much domain knowledge. Integrating that knowledge into the models, into the training process, somehow like a human in a loop, is something I think that generally in transportation is just super impactful, because transportation is, there's so many edge cases, there's so much domain knowledge that kind of just goes into making models that should be generalizable
Yeah.
successful.
And
Totally.
also to build to add on top of that, it increases their own confidence in this model, because they don't see it as something that will replace them and that is or forced upon them, but it's something that they are contributing to, and they know if they're helping it make it better, that it will be right for the task.
I I love that. I love that, having that sort of design for how to involve humans in the loop in
Yeah.
the very beginning, like as part of the training and building the models, so important. I mean, I have my own biases here from my experiences, but I do also tend to think we overestimate the power of these, the power of software and building these models, and sometimes underestimate all the years of experience the experts have built up and how that all works together. So just really love that philosophy of including it in the iteration of the model itself. It's amazing.
Yeah.
Um,
Yeah. Yeah,
well,
CFAR, it's a cool example on how multiple people from multiple backgrounds are collaborating. The
yeah.
idea that you have a sea captain annotating an object detection model is I never imagined it a year ago. So
Very cool. Well, that's a great segue. Holger, why don't you tell us a little bit about, you know, into a bit of the specifics of what you're doing these days at Archer?
Yeah, sure. So at Archer, as a company, what we do is we're building an urban air mobility ecosystem. For that, we're building what's called an electric vertical takeoff and landing aircraft. So say, we're here in the Bay Area, want to take a San Jose to San Francisco trip that usually takes 60 to 90 minutes in traffic. It could be 10 minutes in air, and really saving time in congested areas, and doing that at affordable prices at scale. And so the aircraft takes off vertically like a helicopter, flies wingborne like an aircraft, and then lands again down vertically, but really quiet because it's electric, and so there's distributed electric propulsion. There's not the noise that you're traditionally associated with these really loud helicopters, but rather, right, like we are a new type of aircraft that is much quieter and that can actually be flying in cities without significantly impacting the surrounding environment. And so that's what we're doing as a company. We're building this aircraft, but we're also building the ecosystem around it, an airline, the aerial ride-sharing service that comes with it. And as a data science team at Archer, we sit really centrally, actually, in the organization, helping with a lot of strategic decisions on, we need to decide where do we place infrastructure, for example, for these so-called vertiports, where aircraft can take off and land from rooftops, from general aviation airports. And so, we need to make decisions on where should we place infrastructure? How should we size charging infrastructure? These are fully electric vehicles. So where do we place charging infrastructure? And then, vehicle trade-offs, like should the aircraft fly fast and maybe not as far, or further and slower? So these are all strategic decisions that we help as a data science team with. And then in the long term, eventually we will also be tasked with building the data science services that back the Archer services app, which is, you can think of like dispatching, pricing, all these things that you today have in ride sharing applications like Lyft or Uber or others. And so that's what we do as a team.
Very cool. Well, that's a future I can sign up for, man. I would love to get on a electric vertical takeoff vehicle and get shuttled through traffic.
Yeah, I mean, we're working hard on it, and so we are targeting FAA certification 2024. So you can actually see videos of our demonstrator aircraft flying and online. And so we are targeting FAA certification 2024 and first commercial operation in 2025. So working really hard to make this a reality very soon.
Amazing. Well, in my initial research about like what you're doing, it seems like a lot of your focus on, seems to be a generalized simulation framework to power some of those decisions you were talking about, like where to place vertiports, where to place charging stations. Can you tell us a little more about that?
Yeah, sure. So we have built an in-house software suite, what we call Prime Radiant, that helps us, basically helps us understand how people travel through cities today and how people will or may travel through cities in the future, right? We can never say with certainty how things will evolve in the future, but there's scenarios that we can build out. And so basically we can look at historical trends of how people travel through cities today. There's, for example, in LA, every day there are around 50 million trips, with a trip being someone going from LAX to downtown, someone walking to the grocery store, right? There's 50 million of these trips every day. And we can look at these trips and kind of understand, okay, which of these, will likely go and be more amenable, for example, to urban air mobility by saving them time and other things. And so we can look at, basically we've built this generalizable framework where we model basically travel in cities. And that helps us then make these decisions when we work with stakeholders on decisions like, should we place a vertiport here or here? Is this an animal route, right? We've announced, for example, our New York and Chicago routes. Like, are these routes, right? Are these routes going to be high demand? Will we be able to fit them into future networks where we can have high throughput operations, which will help us to bring prices down, which is really important to us, that we can build this as an affordable service at scale, right? Then, like, basically building like all of these questions we can answer by using tooling that we've developed internally, and that's like what you're referring to there.
If we zoom in just a little to the simulation, and you tell me if I have the wrong mental model, but it seems like you're simulating some certain agents maybe in the real world, and this agent could be maybe a passenger, maybe it's a VTOL operator. Am I missing other agents that are in the simulation?
Yeah, I think one thing maybe to point out is vehicles. Like, we care a lot about, how will vehicles move through cities in the future. So passengers are really important, as you mentioned, and vehicles as well. Like, we really want to understand how will the service look like in the future. And for example, for vehicles, there's in the operations research community, which is kind of a subset of data science that may be less well known than other parts of the data science community. There's a problem called vehicle routing, which it can help kind of understand, okay, how will these vehicles move through cities, and that helps us estimate, right, how, like, throughput, different metrics that we as a company really care about and that we can make decisions based on.
Mm-hmm. Very cool. And how is it? It seems like this sort of chicken and egg problem where, well, the service isn't operational right now, but you still kind of have to have some simulation framework that's able to drive these early decisions. Like, where are you collecting your data from, and like, what are the things out there that you're collecting to help bootstrap this simulation framework?
Yeah, that's a great question, because obviously we do not have the service yet today, right? We have people travel, people move through cities, but people do not yet use eVTOLs that we're building. And so, but what we do have is data on how people move through cities today. So there's basically aggregated, anonymized data on how people kind of move through cities today, based on like, these are there are providers out there that provide data that is aggregated and anonymized, based on I think cell phone use and things like that. But basically it's all we can get data how people move through cities today, and use that in our simulation. And so obviously we need to make sure that that's representative, that makes that, right, we need to really dive in and critically look at that data with a like, before we use it, to make sure that it's representative of the use case. And we look at many different cities so that we get a diverse set of understanding of how people how it is also how people's movements differ in different cities, and how demand differs. And so being really specific about the target markets that we look at, and so that's also really important.
Very cool. So bringing it back a little bit to our earlier conversation about having humans in the loop, Kai's had this great example about, like, okay, ship captains have this expertise built up over the years. They can annotate things that we would miss. Is there a similar example of, who are the experts you talk to when you're building the simulation framework? Is it like urban planners? Is it pilots? Anything surprising there?
Yeah, that's a great point there. And I love bringing it back to the human loop, because like, it's so important in transportation. I think I think so. There's two parts to it. One is when we're building these models. Yes, we are. So we're working. So there's basically cities have transportation demand models that can be incorporated in these models. There are obviously a lot of subject matter experts at Archer that kind of know exactly the vehicle configuration, that know exactly trade-offs on the vehicle side that we incorporate, right? Like, I mean, I talked about charging, right? We have a battery
Yeah.
team that knows better than anyone how this will work, and so we better talk to them, and incorporate, you know, these characteristics that they identify into the models. That's on the input side, so just bringing in subject matter experts there, and kind of, I think, especially with something like this where we're trying to make long-term decisions, it's important to bring people in early and then also like iteratively updating them with results and kind of building trust in the models, right? Because in the end, what we're doing is only as good as we can, as when people trust making decisions based on analysis that they can do with our work. And then I think the second thing is also that the decision makers. So we work a lot with executives at the company because you know, these are long-term, really important decisions. Right? Where do we place infrastructure? That's a lot of money that we're putting down there. And so what's, I think one thing that's important there is, you know, as I said, getting, you know, input early and iterating. Making sure that the inputs in general are sensible. I think we can't control we don't have the counterfactual, and we may only know in like months or years if the decisions we're making are actually the right ones, right? But they're really consequential because we want to build a really highly efficient and very useful to cities and to everyone network, right? We want to build a network that's it serves as many people as possible in an equitable way. We want to build like a network that serves a really really broad spectrum. And so like, in order to build to do that, we need to first like look at the inputs. We can't control the we can't do the counterfactual, but we can control the inputs. We can really work with all the stakeholders on the inputs, look at these assumptions, and then if an output is really sensitive to a certain input, right? Let's say I know like, oh, here, this parameter here, this I don't know, I'm always giving this charging example here, right? Like there's a parameter here that's really important, that where the output is super sensitive to it, right? Then I may really, then I know that as a company, I need to put a lot of focus on getting that thing right, because I know that, all right, if I'm getting like a certain parameter, like timing or whatever down here in my process, it means that, you know, it's going to be really impactful on our system that we're building. I think
that's such an amazing point. Just you know, my previous work, I didn't work directly in the simulation frameworks, but helped the team to do so. And there was always this almost existential, maybe epistemological frustration. It's like you said, the counterfactuals, right? If only I can build the perfect simulation framework that tells me all the counterfactuals, and I can run 10,000 experiments at once, and then San Francisco congestion problems will just go away. And there's kind of this frustration because you know you can't do that. But it seems like what you're saying is the exact outcome is not what you're striving for, but maybe just knowing which parts of the inputs are highly correlated with some shift in the outcome. And all you're saying is like, okay, then the next best thing is to identify those so the business can focus on those and maybe not on the 99 other inputs that may not matter.
Yeah, that's a great summary. And I think then the second part to it is also, you know, as a data science team, we don't make the decision usually, right? We provide, I would almost call it a language to make a decision. Like there's multiple, right? There's a room with multiple executive in it. They want to make a decision. And we provide them with the language, which is we identify the trade-offs that are there and we quantify these trade-offs, right? And then they're able to talk about these trade-offs in a quantifiable way, probe like, what if we change this? What if we change this? And come to a decision through that language that we provide, which is quantifiable trade-offs.
Yeah. It's certainly true in transportation. Sometimes you feel like you fix one thing and then the other thing pops up on the other side, and without a consistent language to describe how all this all interacts with each other, it's quite a mess. Well,
Yeah.
as we're nearing the close, kind of want to get both of your opinion. Maybe, Kai, so we'll go back to you briefly. As we look out into the future, maybe it's this, human in the loop thing, but what advancements do you think will have the biggest impact, or maybe shift in how we do things? Just what are you excited about looking towards the future about ML, AI, and its impact on transportation?
Yeah, from my side, what I see for Seafar and I think for all autonomous ships applications is I look forward to the advancements in edge AI. And so, from one hand, the hardware. I think now there are not much players, and there isn't a lot of. There are some, let's say, investment there, a lot of some improvements there, but like I'm waiting to have like those that one or two perfect AI hardware that wherever you put they will work efficiently.
You
So
want
that's,
waterproof GPUs.
for example, nice. Yeah, I'll write down the idea. Yeah. But also, on top of the hardware, you have also the software challenges that come with it. So model optimization, having high accuracy rate while running the model in real time, um, and yeah. So and also the research in that direction, whether should we continue on improving the models or would the training paradigm change or be optimized in a way that that's enough. So from my side, that's the area of research that I'm most interested about.
Very cool. What about you,
Yeah.
Holger?
Yeah, I think there's I'll start out maybe so from an electric aircraft or eVTOL perspective. Like I think so initially we will be a piloted operator, just certification. We are also a highly regulated space, similar to what Kai said of the shipping industry. The aerospace is also highly regulated, and so we are starting out piloted, but long term, doing autonomous operations, and we're talking here 2030s. Is something that will obviously increase system efficiency a lot, and just also make it kind of be very transformative for the airs I think for the industry, and being able to have these in the long term autonomous. I think autonomy in the general will just transform our transportation systems in a way that we can't even imagine today, right? Like, I mean, first order effects is you're sitting in your car and you're reading a book or something, but second order effects and third order effects of, how will cities transform? How will policy evolve? There's just so many open questions, right? But I think just thinking through these second and third order effects of autonomy is just it will be extremely transformative. I think that's like in terms of what where an ML and AI can have really big impact in transportation. Another kind of I think point is, I think in general, I feel like transportation systems are often defined in their efficiency or in their user experience by like friction points, especially between modes, right? You're taking you're taking a Lyft and Uber, and from the moment that you start walking to you push the button on your phone until you get to the pickup point. Maybe you're in a new spot, you don't know where's the pickup point, so you're walking there first, pushing the button, waiting for 10 minutes, getting your Lyft or Uber, and then taking a 10-minute ride, right? That was a 20-minute ride that could have been 10 basically. And I think that's the same as I've seen in trucking, where the truck drives up to the terminal and sits there for hours because maybe another operator is not there or some paperwork is not signed or things like that. And so I think there's a lot of ways where in these friction points, ML and AI can help a lot with humans in the loop, subject matter experts in the loop, but really really good ETA prediction. And there's a lot of product things as well, right? Like showing someone the way when you walk with an Uber towards an Uber. But at this intersection of building really good models and products that are seamless, I think there's just in every single part of transportation, there's so much opportunity for AI and ML, but it needs to be like really consider all these different edge cases that come up in transportation. And yeah, that's the challenge, but also that's the opportunity, I think.
Totally. And
And I think I want to add something that we as data scientists, we sort of have the responsibility to show the world that these are reliable solutions and reliable technologies.
Mhm.
Because like you have customers visiting your company or future users that are testing your flying car. you It's our job to really create the safe and reliable technology for them to prove to the world and to regulators and to executives that this is the future.
yeah, I always think there's always these really clever designs, not not even just so you can involve annotators in the loop, but for example, showing where the bounding boxes or image segmentation is happening visually, in the car console, so you trust the self-driving
Yeah,
system is not just.
yeah.
There's all these things that we have to do to make these seem extremely robust beyond just making it more accurate all the time. It's such a great point. Yeah. I certainly will want that when I'm in the VTOL. I'm going to want to know what it's
Yeah.
detecting, what's going
Wait
on.
for me, yeah.
Well, thank you so much for taking the time. And I hope for those in the audience can really get a sense of just how much AI and ML permeates every aspect of these sort of transportation systems. I mean, we touched on things that are on the edge compute, on the vehicles themselves, all the modeling and simulation goes into the infrastructure supporting these decision points where to put variable ports, not to even mention the real-time aspects of it. Just a tremendous space for ML and AI to really make a huge difference. And thank you both for sharing that with us today.
Yeah, thank you, Harrison.
Thanks for having me.